what I want to do in this video is give a very high-level overview of the four fundamental forces of the universe. And I'm going to start with gravity. I'm going to start with gravity. And it might surprise some of you that gravity is actually the weakest of the four fundamental forces. And that's surprising because you say, wow, that's what keeps us glued, not glued, but it keeps us from jumping off the planet. It's what keeps the moon in orbit around the Earth in orbit around the sun in orbit around the center of the Milky Way galaxy. So it's a little bit surprising that it's actually the weakest of the forces. And that starts to make sense when you actually think about things on maybe more of a human scale or a molecular scale or even an atomic scale. Even on a human scale, your computer monitor and you have some type of gravitational attraction, but you don't notice it. Or your cell phone and your wallet, there's gravitational attraction, but you don't see them being drawn to each other the way you might see two magnets drawn to each other or repelled from each other. And if you go to even a smaller scale, you'll see that it matters even less. We never even talk about gravity in chemistry, although the gravity is there. But at those scales, the other forces really start to dominate. So gravity is our weakest. So if we move up a little bit from that, we get, and this is maybe the hardest force for us to visualize, or at least the least intuitive force for me, is actually the weak force. The weak, sometimes called the weak interaction. And it's what's responsible for radioactive decay, in particular beta minus and beta plus decay. And just to give you an example of the actual weak interaction, if I had some cesium 137, 137 means it has 137 nucleons. A nucleon is either a proton or a neutron. You add up the protons and neutrons of cesium, you get 137. And it is cesium because it has exactly 55 protons. Now, the weak interaction is what's responsible for one of the neutrons, essentially one of its quarks flipping and turning into a proton. And I'm not going to go into detail of what a quark is and all of that. And the math can get pretty hairy. But I just want to give you an example of what the weak interaction does. So if one of these neutrons turns into a proton, then we're going to have one extra proton, but we're going to have the same number of nucleons. Instead of an extra neutron here, you now have an extra proton here. And so now this is a different atom. It is now barium. And in that flipping, it will actually emit an electron and an anti-electron neutrino. And I'm not going to go into the details of what an anti-electron neutrino is. These are fundamental particles. But this is just what the weak interaction is. It's not something that's completely obvious to us. It's not kind of this traditional things pulling or pushing away from each other like we associate with the other forces. Now, the next strongest force, and just to give a sense of how weak gravity is, even relative to the weak interaction, the weak interaction is 10 to the 25th times the strength of gravity. Times the strength of gravity. And you might be thinking, if this is so strong, how come this doesn't operate on planets or us relative to the Earth, or the reason, why doesn't this apply to intergalactic distances the way gravity does? And the reason is the weak interaction really applies to very small distances. Very small distances. So it can be much stronger than gravity, but only over and it really only applies on the subatomic scale. You go anything beyond that, it kind of disappears as an actual force, as an actual interaction. Now, the next force up the hierarchy, which is one that we are more familiar with. It is something, it's what actually dominates most of the chemistry that we deal with, and electromagnetism that we deal with, and that's the electromagnetic force. We write it in magenta. Electromagnetic force. And just to give a sense, this is 10 to the 36 times the strength of gravity. 10 to the 36 times the strength of gravity. So it kind of puts the weak force in its place. It's 10 to the 12th times stronger than the weak force. So these are huge numbers that we're talking about, either this relative to that or even this relative to gravity. And so you might be saying, well, the electromagnetic force, that's unbelievably strong. Why doesn't that apply over these these kind of macro scales like gravity. Let me write there, macro scales. Macro scales. Why doesn't it apply to macro scales? And it actually, there's nothing about the electromagnetic force why it can't, or it actually does apply over large distances. The reality, though, is you don't have these huge concentrations of either Coulomb charges or magnetism the way you do mass. So the mass, since you have such huge concentrations, it can operate over huge distances, even though it's way weaker than the electromagnetic force. The electromagnetic force, what happens is because it's both attractive and repulsive, it tends to kind of sort itself out so you don't have these huge concentrations of charge. Now, the other thing you might be wondering about is, why is it called the electromagnetic force? In our everyday life, there's things like the Coulomb force, or the electrostatic force, which we're familiar with. Positive charges or like charges want to repel. If both of these were negative, the same thing would be happening. And different charges like to attract. We've seen this multiple times. This is the Coulomb force, or the electrostatic force. Electrostatic. And then on the other side of the word, I guess, you have the magnetic part. And magnets, you've played with magnets on your fridge. If they're the same side of the magnet, they're going to repel each other. If they're the opposite sides, opposite poles, they're going to attract each other. So why is it called one force? And it's called one force, and once again, I'm not going to go into detail here. It's called one force because it turns out that the Coulomb force, the electrostatic force, and the magnetic force are actually the same thing viewed in different frames of references. So I won't go into a lot of detail, but just keep that in the back of your mind that they are connected. In a future video, I'll go more into the intuition of how they are connected. It deals with it's more apparent when they're when the charges are moving at relativistic frames, and you have, well, I won't go into a lot of detail there. But just keep in mind that they really are the same force, just viewed from different frames of reference. Now, the strongest of the force is probably the best named of them all, and that's the strong force. That is the strong force. The strong force. And although you probably haven't seen this yet in chemistry classes, it actually applies very strongly in chemistry. Because from the get-go, when you first learn about atoms, let me draw a helium atom. A helium atom has two protons in its nucleus, and it has two neutrons. And then it also has two electrons circulating around. So it has an electron, and I could draw the electrons as much smaller. I won't try to do anything in relative size, but it has two electrons floating around. And one question that may or may not have jumped into your mind when you first saw this model of an atom is like, well, I see why the electrons are attracted to the nucleus. It has a negative Coulomb charge. The nucleus has a net positive Coulomb charge. But what's not so obvious, and that what tends not to sometimes be explained in chemistry class, is these two positive charges are sitting right next to each other. If the electromagnetic force was the only force in play, if the Coulomb force was the only thing happening, these guys would just run away from each other. They would repel each other. And so the only reason why they're able to stick to each other is that there's an even stronger force than the electromagnetic force operating at these very small distances. So if you get two of these protons close enough together, and the strong force only applies over very small distances, subatomic, or I should even say subnucleic distances, then the strong interaction comes into play. So then you have the strong interaction actually keeping these charges together. And once again, just to keep it in mind relative to gravity, it is 10 to the 38th times the strength of gravity. Or it's about 100 times stronger than the electromagnetic force. So once again, the reason why you don't see the strong force, which is the strongest of all of the forces, or the weak interaction applying over huge scales, is that they really their strength dies off super fast. Even when you start going to large radius nucleuses of atoms, the strength starts to die off, especially for the strong force. The reason why you don't see the electromagnetic force operating over large distances, even though in theory it can, like gravity, is that you don't see the type of charge concentrations the way you see mass concentrations in the universe. Because the charge concentrations tend to sort them out. They start to equalize. If I have a huge positive charge there and a huge negative charge there, they will attract each other and then become essentially a big lump of neutral charge. And once they're a big lump of neutral charge, they won't interact with anything else. In gravity, if you have one mass and another mass and they attract each other, then you have another mass that's even better at attracting each other at other masses. And so it'll keep attracting things to it. So it kind of snowballs the process. And that's why gravity can operates on these really, really large objects in our universe and in the universe as a whole.